Hey, hello everyone. Welcome to our seminar for the AMC 10 and AMC 12, since the contest is coming up, and we will be covering various concepts to help you guys prepare for it. So let's get started with our first concept, which is on 30, 60, 90 triangles. Now this is a special right triangle in which the ratio of the sides are always 1 to the square root of 3 to 2, and this will always be true for all 30, 60, 90 triangles. Pretend the side opposite to 30 is x, then that means the side opposite to 90 degrees will always be 2x, and the side opposite to 60 degrees will always be x times the square root of 3. So now, this is our first problem, example problem, which we'll be using a lot of 30, 60, 90 triangles. So let's get started with it. So it says, let A, B, C, D, E, F be a regular hexagon with a side length of 1. Denote by X, Y, and Z the midpoints of side AB, CD, and EF respectively. What is the area of the convex hexagon whose interior is the intersection of triangle ACE and XYZ? So that means we need to find this weird region. Well, the easiest method is in a lot of these problems, you take a bigger area, you calculate the bigger area, and you subtract the smaller areas, and that's what we're going to be used. We're gonna try to calculate the area of ACE and subtract the areas of these three smaller right triangles. So let's get started. So for any regular hexagon, the angle measure will always be 120 degrees, because the formula to find the total angle sum is n minus 2 times 180, where n represents the number of sides, and in this case the number of sides is 6. So 6 minus 2, which is 4. 4 times 180, which is 720. And in a regular hexagon, they're all equal, the angles. So all you do is divide this by the number of angles that we have, which is 6. So we know all of these angles B, A, F, and E, D, C, they're 120. And now, this is the most important part. If you draw a line perpendicular to AC, and it will bisect the angle ABC, which means it divides it in half. So if it's perpendicular, we know this is 90, and if it divides it in half, this is 60, and we know this is 60, we know this is 90. Also, we know that this is now 30 because a triangle's angle measure has to add up to 180. So we know this has to be 30, and same for here. What else do we know? We know that the side lengths are 1. And now, we will use this to try to find AC, which is the length of the equilateral triangle ACE, and that is the triangle we will be using. How will we find the area? So for that, we need to use 30, 60, 90 triangles. So if the side opposite to 90 is 2x, then we know 2x equals to 1. That means x equals to 1 over 2. That means the side opposite to 30 is just x, which is 1 over 2. So this side is 1 over 2. The side opposite to 60 degrees is x times the square root of 3, which is 1 over 2 times the square root of 3, which means this thing a, and this is the midpoint. Let's say this is let's say this is g. So the AG is just square root of 3 over 2. That means AC is square root of 3 because you multiply by 2 to get the entire length. That means AC is just square root of 3. And now we're going to try to find the area. Another thing we know that AFE, this angle, has 30 degrees. The angle measures 30 degrees. And if you draw a bisector that bisects angle AFE, it's the same triangles as this one. They're all the same, which means the side lengths will also apply over here. We know that this length, so if this is 1, we know this is 60 degrees, this is 90 degrees. We also know that the length of this is square root of 3 over 2. Yeah, when it comes to 30, 60, 90 triangles, the diagrams will be a bit messy, but I'll make it clear. So we know that the angle measure, so we know this is 90, this is 60 over here. So if the side opposite to 90 is square root of 3 over 2, that means the side opposite to 30 is just half of that. That means the side opposite to 30, AP, is just square root of 3 over 4. And we want the height of this triangle. And the side opposite to that is just square root of 3 times the side opposite to 30, which means square root of 3 times this is just 3 over 4. And that's the base and the height of the triangle. And now to find the area of the smaller triangle, you just go 1/2 times this and times this. And now we have to compute this. We get 3 times the square root of 3 over 4 times 4, which is 16 over 2, 32. But this is just the area of one small triangle. And we have 3 of those, and they're all congruent. So instead of labeling all the sides, we just multiply this by 3. So 3, all of this multiplied just makes the 3 times 3, which is 9. So that's the area we want to subtract from the area of triangle ACE. We know ACE is an equilateral triangle, and its side length is square root of 3. And the formula to find the area of an equilateral triangle is just square root of 3 over 4 s squared, where s is the side. So we will multiply s, which is s squared. We will square the side and then multiply it to square root of 3 over 4. And if you square this, you get 3. So the area of the equilateral triangle is just 3 times the square root of 3 over 4. And now we will subtract 9 times the square root of 3 over 32 from that. So you take the so now I'm going to erase this and solve the problem. So we know that the LCM is 32. And after you compute it, you multiply by 8 over there on the top, you get 24 times the square root of 3 minus 9 times the square root of 3 divided by 32. And this equals to 15 times the square root of 3 divided by 32. Now this shows the importance of 30, 60, 90 triangles on the AMC 10 and AMC 12, because it made this problem, and it was like a problem 24 from the AMC 10. It made it pretty simple because it's just computation at the end. So it shows the importance. Now our next topic, it is that opposite angles in any cyclic quadrilateral, they sum to 180 degrees, no matter what, opposite angles. They will always sum to 180 degrees. And a cyclic quadrilateral is a quadrilateral which has it's all of its vertices on the circumference of the circle. So in this problem, it says, in the given circle, the diameter EB is parallel to DC. The fact that they're parallel will matter to us. It matters a lot, and you'll see why. It says the angle AEB and ABE are in the ratio of 4 to 5, which means if this is 4x, then this will be 5x. Now, it's asking us for the angle measure of BCD. Now, to find that angle measure, we know that the diameter EB is the diameter. Now that is very important for solving this problem, because we know that this angle is 90. Because if a triangle is inscribed in a circle and and pretend it's a right triangle, if any right triangle is inscribed in a circle and the diameter is the hypotenuse is the diameter, we know it is a right triangle. So this is 90 degrees no matter what. Now we know that these other angles sum to 90. So 4x plus 5x equals to 90, which means 9x equals to 90. Now you divide both sides by 9 and you get x equals to 10. That means this angle is just 40 and that other angle is 50. So this is 40 and this is 50. And it says that AB is parallel to ED, and now that's where the concept comes in. Because if two lines are parallel and you have a transversal that goes through it, pretend AB and ED are the parallel lines, EB is the transversal, then alternate interior angles are always congruent. You need to know this theorem. And if alternate interior angles are congruent, we know if this is 50, then this is 50. And if this is 50, then it's asking us to find the angle measure of BCD. And you notice this is EBCD is a cyclic quadrilateral. That means BEC, angle BEC plus the measure of angle BCD has to be 180. And we know one of them is 50 degrees. That means the other has to be 130 degrees, and that is the answer. So this shows the importance of knowing the fact that opposite angles in a cyclic quadrilateral sum to 180 degrees. Now the next problem, and this problem has a very elegant solution. So it says, extending lines, it's a very common technique on the AMC 10 and AMC 12. For many complicated problems, before trying to apply theorems or doing anything in general, first try to draw stuff out and make it a very simple shape. And this example is the best example that you can find. supporting the idea. So you can find random lengths by making longer ones and subtracting shorter ones. For example, in this problem, it says we have a square ABCD with side lengths of 13, which means these are all 13. And it says points E and F are exterior to the square. That just means they're outside the square. And such that BE equals to DF, which equals to 5, and AE equals to CF equals to 12. Well, the trick to this problem, we want to find EF squared. And that looks pretty complicated at first. However, if this is 13, we already have 2 5, 12, 13 right triangles. What if we make more of those? Let's try to make more. What if we just extend this line over here and extend this here and make another 5, 12, 13 right triangle here? And we do the same for the other side. And we get 5 here and 12 here. And you see, we just turned this complicated looking shape into just a simple square. And now we know the side lengths are 17. So EF is just 17 squared plus 17 squared. And we could square root that, but there is no point because you're going to square it anyways. And if you just, and that's just going to mean extra calculation. And this is 289 plus 289, which is 578. And that is the answer. So it is very important before just drawing the problem or doing anything. Just think about it, like draw some things inside the shape and try to find a very elegant solution. Now our next problem, and this will bring in a very, very important concept, which is this theorem. It says that if you multiply the diagonals of any cyclic quadrilateral, then the value of that is the same as multiplying opposite sides of the quadrilateral and adding them. For example, pretend this is a cyclic quadrilateral, just as an example, and this is a diagonal, and this is a diagonal, and this is A, this is B, this is C, this is D. So all this theorem says is that AC, okay, this is messy. Okay, so all this theorem says is that BD times AC equals to AB times DC plus AD times BC. And this will always be true for any cyclic quadrilateral. And now I'll show you an example problem. So it says a quadrilateral is inscribed in a circle of radius 200 times the square root of 2. 3 of the sides of this quadrilateral have length 200. And now it's asking us to find the 4th side. And the lengths that are 200 are BC, BA, and CD. So we know those are 200. 200, this is 200, and this is 200. Now we want to find the length of AD. If you notice, it says that the quadrilateral is inscribed. And an inscribed quadrilateral means it's a cyclic quadrilateral. And now we can use this theorem. It says that now we will multiply the diagonals to each other, which is BD and AC. Okay, so BD times AC has to equal to will always equal to BC times AD plus BA the opposite sides, if you multiply them, it has to equal to that. Oh, oops. I accidentally put in the wrong symbol. So this will always be true for any cyclic quadrilateral. The diagonals will equal to the opposite sides multiplied to each other and then added, and this will always be true. So for this problem, now let's try to use this theorem to actually solve the problem now. I'll make some space here. Okay, so we don't know BD yet or AC yet. So let's just leave it blank for now. But we do know BC, we know 3 of the sides. BA and CD are just 200, which means 200 times 200 is 40,000. And then we want AD, we don't know AD. I'll just say it's X for now. That means 200x plus 40,000. Now, to solve the problem, there is one way. For example, you know BD. If you BE is just half of BD, and BE is one of the heights of triangle BOC. So that means if we find the area of BCO, you can just divide it by CO, which is the base, and we know that is 200 times the square root of 2. Remember, pretend if you have a triangle here, like this is a right, like I'll show you an example, and we know this is, pretend this is 3, this is 4. Then this is not the only method of finding the area, 1/2 times 3 times 4. You could also use this, the base, which is 5, and this height over here. So this is the method we'll use in this problem to try to find BD and AC. So we know BE. So now we're gonna find the area of BCO. So we know this is an isosceles triangle, and a very simple way for an isosceles triangle is just to simply draw a perpendicular line to the base, and we know that it will divide the side length in half. So this 200 will just become 100 and 100. Now we know that BO is just the radius, which is 200 times the square root of 2. And now we can just use some simple Pythagorean theorem to find the height. So we know that the Pythagorean theorem states that the hypotenuse squared equals to the leg squared plus the leg squared. And 200 times the square root of 2 squared is just 80,000. Because 200 times 200 is 40,000, and square root of 2 times square root of 2 is just 2. So 80,000 equals to 100 squared, which is obviously 10,000, plus, let's just call this y, plus y squared. So you subtract 10,000 from both sides to get 70,000, and that is y squared, and we want to find y. We can simply do that by square rooting both sides, and after you do that, we'll find that y equals to 100 times the square root of 7. And now we need to find the area of the triangle. And the area of the triangle is 1/2 times the base times height. We know the base is BC, and the height is the y length, which is 100 times the square root of 7. The base is 200, and you multiply this by 1/2. And then you get 100, because this becomes 100, times 100 square root of 7. So 100 times this, and that is the area of the triangle we're talking about. So after you compute this, you get 10,000 times the square root of 7. Now the method to finding BE is actually pretty simple. People are asking x. X is the length of BE, not the height of the isosceles triangle, because a triangle has multiple heights. I'm talking about the other height, the longer one. BE is the other height that we want to calculate. The height we just calculated is the other height. Yeah. So from here we know the area is 100 times the square root of 7. So we know the area of the triangle is also CO times BE times 1/2. So we're gonna rewrite this. So 1/2 times the radius CO, which is 200 times square root of 2. We don't know BE, but we said it's x here, so times x. And it's supposed to equal to this. Now, this just becomes 100 times the square root of 2, and you divide both sides by that, and you get this. 10,000 divided by 100 is just 100. And then we have this, and we rationalize it, which means multiplying it by multiplying the denominator thing, the term there, by the to the top and the bottom. And after you do that, you get something like this. And you see that this just becomes 2. So after that, it becomes 7 times 2, which is 14. 100 times the square root of 14 over 2, which simplifies to 102, just cancel out to 50. So we know the side length is 50 times the square root of 14. That is BE. And BD is just double that. That means BD is actually 100 times the square root of 14. And then AC is the same thing, because these triangles are the same, the heights. And after that, you put this back here into this equation. So 200 x, I'll erase this So now we know that the equation is just 200x plus 40,000, which equals to 140,000, because 100 times square root of 14 times 100 times square root of 14, and that is what we need to calculate. So after that, you subtract both sides by 40,000, and you get 200x equals to 100,000. And after dividing, you'll get x equals to 500. I mean, not x, I mean the whole thing, it will be 500. Yeah, wait. Yeah, so I'm sorry, yeah, 80 is just 500 at the end, because of this theorem. 200x equals to 10,000. And this shows the power of cyclic quadrilateral. Yes, people are right, this theorem takes a bit longer, but for some problems it's actually the fastest solution, and this was a really good example to show this theorem, which is why I chose this problem. Yes, there are other methods of trying to find the answer, but I wanted to demonstrate this theorem. So the next problem is the two tangent theorem. This theorem is actually not that complicated. So all it states is that if two tangent lines intersect at the same point, then they have the same length. For example, I'll show you what I mean. So pretend I have a circle here, and this is the tangency point of one line, and this is the tangency point of the other line. So all this theorem states is that if they meet at the same point, then they are congruent. Note that it's only congruent from the point where they meet to the tangency point. So if the line all the way goes here, then it's not congruent to that. It's congruent to the tangency point. That is the most important part that you should remember. So in this problem, it says square ABCD has a side length of 2. So let's label it. And it says a semicircle with diameter AB is constructed inside the square, and the tangent to the semicircle from C intersects side AD at A. So this is the tangency point. Now it's asking us for the length of CE. Whenever you have a tangency point, a trick here is to connect the tangency point to the center, which is this. And then we notice this is just a lot of two tangent theorems here. Pretend this is point F. CF and CB are tangents to the circle, and they meet at C. And we know CB is 2, that means CF is 2. However, we don't know EA, so we're going to call it X. If EA is X, that means EF is also X. And that means DE is 2 minus X. And now we can just apply the Pythagorean theorem to find X. That means 2 squared, which is 4, plus 2 minus X squared, which is 4, plus X squared minus 4X. This equals to 2 plus X squared, which is X squared, plus 4X plus 4. Don't mind this part. And then we need to compute this. The X squares cancel out. The 4 plus 4, 8. You subtract 4 from both sides, you get 4 equals to 8X. And then you divide both sides by 8, and you get X equals to 1 over 2. And it's asking us to find the length of CE, which is just CF plus EF. And we know CF is 2, and EF is X, which is 1 over 2. So the answer is 2 plus 1 over 2, which equals to 5 over 2. And now we found the answer. This was like one of the last problems from, this was like the final 5 from that year. And look, we cracked it out with just the two tangents theorem. So it's a very important concept. Now, we're going to go into similar triangles now. And before we do, let's discuss how to identify similar triangles, which is the most important part. So we know AA similarity. That's just if two of the angles in two triangles, if they are congruent, then it means that the third one is also, which makes the triangle similar. This is actually, this is just a common sense theorem. For example, two angles are X and the other is Y. And that's the same for two triangles. Then the other side of the other angle will always be 180 minus X minus Y, no matter what. So this works for all triangles. Now SAS stands for side angle side. In this, if two sides have the same ratio, and the angle between those sides are congruent, then the triangles are similar. So in this case, we see that 50 and 50. Now, this will be similar if these ratios are the same. So we see that the ratio to FD to AB is just 12 over 8, and that's the same thing for FE to CB, 24 over 16. Now we'll simplify this to see if they are the same ratio or not. This is 3 over 2, and this is 3 over 2. The ratios are the same. The angle in the middle is also the same. That means they are similar. Now the last way to identify similar triangles is SSS, which stands for side 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 similarity, and it tells us that if all of the sides of two triangles are in the same ratio, then they are similar triangles. This just means that an example would be pretend these are the side lengths of a triangle 3, 4, 5, and the other triangle is 6, 8, 10. Then the ratio is always times 2. You just multiply by 2, multiply by 2, multiply by 2 to get the other triangle, so they are similar. Now this is a great example of, it's not that basic because it involves drawing similar triangles yourself. For example, some problems will have the similar triangles given in the shape, while in some you'll have to draw them out. So in this problem it says, in the adjoining figure, two circles with radii 8 and 6 are drawn from their centers, with their centers that are 12 units apart. At P, one of the points of intersection, a line is drawn in such a way that chords QP and PR are of equal length. Now we want to find the square of the length of QP. Even though this is a problem 14 from the AIM, it is very hard, but with the solution I'm going to show, it's actually not hard at all. So there's a property that in all isosceles triangles, if you draw an altitude to the base, it's also a bisector of the side of the base, and it bisects the angle on top. That means it divides the base into two equal parts. That means let's try to go for isosceles triangle hunting and then apply similar triangles. So whenever, let's just connect the points to the center and hope we find something clever. So now we drew this triangle, and it's clearly isosceles because two of the sides are the radius. Pretend this is F. So QF and PF are just the radii of the circle, which are 8. Now, if we draw a perpendicular line to QP, the theorem states that it divides this into two equal parts. That means, pretend this is S. That means QS equals to SP. Now let's do the same for the other triangle here. Let's extend this point to R and connect P all the way to the center. And let's pretend this is T. We know that PT and RT are the radii of the circle, so they are of equal length, 6. And if you draw a perpendicular line to PR, then it divides PR into two equal parts, which makes this equal and equal. And we know that QP and PR are equal, so pretend if QS is X, that means SP is X, and that means let's say this is U, PU is X, and UR is X. They're all X. Now, if you look very closely at the diagram, we have a 90-degree angle here because this is perpendicular, as I said. Now I will show you the clever solution to this problem. Now you notice that these are 90 degrees. RSF is the triangle, and RUT. One thing we notice is that this angle is shared by both of the triangles. And we know that the other angle is 90. That means they are similar triangles. RUT and RSF are similar triangles, which means the ratios of all the sides will always be the same. For example, we know the ratio, we just take the, so for example, RT is 6, and RF is the hypotenuse of the other triangle. It's 12 plus 6, which is 18. That means the ratio is just 1 over 3. That means if UT is Y, then SF is 3Y. And now it's simple algebra, because we know this is 90 degrees. That means x squared plus 9y squared equals to 8 squared, 64. And same here, x squared plus y squared equals to 36. Also, remember that we want to find the length of QP, and we took half of that length, which is x. So at the end, we want to find 2x, but we want to square it. You should always write it on the side so you don't forget what you're trying to find. So now let's get back. So we know we found these two Pythagorean theorem relationships, and now this is just a system of equations. If you subtract this, the x squareds cancel out, and that leaves 9y squared minus y squared, which is 8y squared, which equals to 64 minus 36, which is just 28. That means y squared equals to 28 over 8. And now it's time to simplify this. You divide both sides by 4, and you get 7 over 2. And that means y squared equals to 7 over 2. And we're just going to substitute this back in here to find the x squared. So 36 minus 7 over 2 equals to x squared. And then, 36 is 72 over 2 because you take the LCM. That means x squared equals to 65 over 2. And x equals to the square root of 65 over 2. And what we want to find is 2 times this squared. So 2 times the square root of 65 over 2 squared. 65 over 2, yeah. So if you square this, 2 times 2 becomes 4. The 65 over 2, the square roots just cancel out. So it's just 4 times 65 over 2. And we see that 4 and 2, it reduces. This becomes 2. So 2 times 65, it becomes 130. Yes, you could use other theorems like maybe power of a point, but I wanted to show you an example of similar triangles where you make similar triangles. Like in the problem, it's not obvious, but then you have to construct them by yourself. Okay, so the next problem, it's a very good example of the angle bisector theorem. So if a ray bisects an angle of a triangle, then it divides the opposite sides of the triangle into segments that are proportional to the two other sides. For example, in this diagram, I'll expand it so you guys can see it. So this is a ray, and it bisects this angle. So all this says is that A over C will be equal to B over D because of the angle bisector theorem, and it's something that is very important to know. So now let's try this challenging problem using this theorem. So it says in triangle ABC, as shown in the figure, we have AB is 7, BC is 8, and CA is 9. It says AH is an altitude, and an altitude means that these angles are 90. Okay, now it says points D and E lie on side AC and AB respectively, over here and over here, so that BD and CE are angle bisectors. So this bisects this angle, these two are the same, and it also bisects this angle, intersecting AH at Q and P. And now it's asking us to find PQ. And now we will be using a lot of angle bisector theorem here. So we want to find the length of AH because PQ is inside AH. So what if we find AP or like QH and just subtract it to find PQ? So let's try that. So how will we find AH? Well, if this is an altitude, if we know the area of the triangle, then we can find AH because 8 times AH times 1 over 2 equals to the area of the triangle. So we know we have 9, 8, 7. In this case, this is not a right triangle or something, so we will use something called Heron's formula, where S is the semi-perimeter, and it says S minus A, S times S minus A, S times S minus B, times S minus C is the area of any triangle if the side lengths are A, B, and C. So in this case, we want to know the semi-perimeter, which is the perimeter divided by 2. So 9 plus 8 plus 7, and that brings in 24. That means the semi-perimeter is 24 divided by 2, which is 12. So square root of 12 times 12, and then you subtract all the side lengths. So 12 minus 9, 3, 12 minus 8, 4, and 12 minus 7, which is 5, and that is the area of the triangle. So now we're going to compute this. So we know 12 times 3 times 4, which is 12. So this is just, we can just take the 12 over here, because this is 144 times 5, and 144 is 12, if you square root that. So 12 times the square root of 5 is the area of the triangle. And if you turn this diagram around and look, the area of the triangle is also CB times AH times 1 over 2. That means 1 over 2 times 8 times AH equals to 12 times the square root of 5. And we know that 1 over 2 times 8 is 4. So it says 4 times AH equals to 12 times the square root of 5. And now you divide both sides by 4 to find the height, the altitude. And you get 3 times the square root of 5. And now we're going to be applying a lot of angle bisector theorem in this problem. I'll show you. So we'll need a lot of space. So we know this altitude is just 3 times the square root of 5. We know this is congruent and this is congruent. So now we know that because of the angle bisector theorem, AB over AQ equals to AH over QH. I mean BH, sorry. BH over QH. And now we know that AB is 7 and BH, we don't know BH yet, so we're gonna find that out. Since this is 3 times the square root of 5 and we know this is 9, we can use the Pythagorean theorem because this is a 90-degree angle. So 9 squared, which is 81, minus 3 times the square root of 5 squared, which is 3 times 3, which is 9, times the square root of 5, 45, equals to, this is equals to 36, but that's the square of the length, which means if you square root that, that's when you get CH, which means CH is just 6, and we know CB, the entire thing is 8, so HB is obviously 2. So now using the angle bisector theorem, it says 7 over AQ equals to 2 over QH. So 7. And now we will substitute values in for AQ and QH. Like we know that pretend QH is x. That means AQ is just 3 times square root of 5 minus x. So 7 over 3 times the square root of 5 minus x equals to 2 over x. And now you multiply both sides by x first, and you get 7x equals 2. And now and then you multiply this thing to both sides to remove the denominators, obviously. So you get 6 times the square root of 5 minus 2x. Now you add 2x to both sides to get 9x equals to 6 times the square root of 5. And you divide both sides by 9 to get x. And after that, you simply get 2 times the square root of 5 over 3. And that is the length of QH. And now let's try finding the length of AP. So let me circle this as equals to QH. So let me remove my work here so we can try to find the other length. Okay, so now we're gonna see that this length over here, I'll highlight it. This length over this length equals to this length over this length because these two angles are are the same because of the angle bisector theorem. So 9 over, we don't know AP, let's say it's y. So 9 over y equals to, we know this length is 6. So 6 over 3 times the square root of 5 minus y. Now you multiply and you're going to remove the denominators, which obviously by multiplying by y, then multiplying by this other denominator. And after you do so, you get 27 times the square root of 5 minus 9y equals to 6y. And now you add 9y to both sides to get 27 times the square root of 5 equals to 15y. And you divide 15 from both sides and reduce, you get 9 times the square root of 5 over 5. And that's the length of AP. And we want PQ. We know what AH is. We know what QH is. That means PQ equals to the whole length minus AP minus QH. And we know the whole length is just 3 times the square root of 5. So we will subtract all of these now. Minus 2 times the square root of 5 over 3 minus 9 square root of 5 over 5. So now we will take the common denominator to simplify this expression. So 15 is the denominator because you take the LCM. and now it's just computation. 45 times the square root of 5 minus 15, and then now this is just 45 times the square root of 5 minus 10 times the square root of 5 minus 18 times the square root of 5. And after you simplify, you get 17 times the square root of 5 over 15 as the length that we wanted. So this shows the power of angle bisector theorem. This was one of the towards the end problems, but with the angle bisector theorem, it was just computation. So now this concept brings in a very important problem and a concept. So a triangle area can be found out with the inscribed circle. The radius of the inscribed circle times half the perimeter of the triangle is equal to the area of the triangle. For example, in this problem, it says triangle ABC, in which ABC, and these are the side lengths, and it says D is the midpoint of BC. It says, what is the sum of the radii of the circles inscribed in triangle ADB and ADC? This problem can be actually pretty tricky, but if you know this concept, it's really easy. So this is the midpoint of, this is D, and now it wants to know the sum of the inscribed circles. Which can be found out through this theorem that I just told you. So now we're going to compute the areas. So this is 5, BD is 5, and DC is 5. We know that if we draw a line perpendicular to this, we will divide this to 2 equal parts and get right triangles here. And we know this is 5, this is 4, this is obviously 3. The same thing applies to here. We know this is 4 because this is just a rectangle, and then this is 3, and this is 3. Now we can use the inscribed circle times half the times the perimeter. The radius times the semi-perimeter to find the area of the triangle. So we know that the area of ABD is just 1/2 times 6 times 4, which is literally just 12. So 12. And this theorem states that 12, you can compute this area by the semi-perimeter times the radius. So the radius is R1 times the semi-perimeter, which is just 6 plus 5 plus 5, which is 16. And you divide both sides by 16 to get R1 equals to 3 over 4. And you reduce it all. So obviously, now we will do this for the other triangle. So the area is the same thing because they're just 2, 3, 4, 5 triangles slapped together. So it's just 12 equals to R2 times the semi-perimeter, which is 5 plus 5 plus 4 plus 4, and you divide that by 2 to get 9. And then you divide both sides by 9 to get R2 equals to 4 over 3. And now it wants the sum of these radii. So 3 over 4 plus 4 over 3. You take the LCM first, 9 plus 16, and then you get 25 over 12, which is the answer. So this shows the importance of knowing so this shows the importance of knowing this theorem, that the area of a triangle is also the semi-perimeter times the Oh yeah, someone just pointed out something. I just made a mistake. Sorry. Yeah, the semi-perimeter is not 16, it's actually 8. So you divide both sides by 8 to get 4 over 3. I'm very sorry, I just made a mistake. So this is 4 over 3. I just made another mistake. This is actually 3 over 2. This is 3 over 2 plus 4 over 3. Since the other radii is... so 3 over 2 plus 4 over 3. Now the common denominator is 6. And after computing this... so after computing this, you get 17 over 6, because you add the radii. So it's the semi-perimeter, which is half the perimeter. Just don't make a mistake like I just made. It's actually half the perimeter, so it's 8, not 16. So now the next problem. So sometimes when you have a very complicated figure, you can actually find the answer by transforming the figure, which means rotating it, reflecting it, and those other things. like that with different transformations. And this problem is a very good example of that. So it says that ABC is an equilateral triangle with a side length of S, with the property that there is a unique point P inside the triangle such that AP equals to 1, BP equals to square root of 3, and CP equals to 2. Note that I drew this, I got the figure from before because it's very hard to draw this diagram on a computer. So after that, all I did was I rotated this figure by 60 degrees because we noticed that 1, 2, and the square root of 3. This is literally just a 30, 60, 90 triangle pair. And we want a 60 degree angle and to hope to find a 30, 60, 90 triangle. So I rotated it by 60 degrees. And after that, if you rotate it by 60 degrees, we know that this is 60 degrees. We already know this is 1, as it's stated, and this is 1 because of the rotation. And because of that reason, this is also 1, because it's just an equilateral triangle. And now, we notice that 1 times square, we have the right triangle we wanted after rotating it. This is 90, this is 30, and this is 60, because of the 30, 60, 90 triangle pair. So we got these angles. And now, we still don't have the answer we want. And in that case, we rotate it once more to the other side. And after that, we will most likely get the answer. So we know this is, so the other points just come over here. We notice that we get square root of 3 here. We also make 1 here. Okay, this I will show you another solution to this problem after, and show you the importance of the other solution. This solution is very complicated, and you can easily get it wrong. And I am not a fan of this solution. So after rotating it to 60 degrees counterclockwise, we get this diagram, which is simply just we know this is 60 degrees because of rotation. This is 1, and this is 1. Through that, we know this is 90 degrees, because if this is 1, this is square root of 3. We know this is 2 because of the rotation. This is 90 degrees. Now we know this is 90 plus 60 plus 60 plus 60, which is 180 plus 90, which is 270 degrees. That means 360 minus 270 is 90. So this is a right angle. And we want to find the side length, BC. And if this is a right angle, we know that's square root of 3 squared, which is 3, plus 2 squared, which is 4. You square root that to get the side length, which is the square root of 7. I understand that this solution is very crazy. It's actually very hard, so I'm going to show you another solution. So for this problem, this has another solution. Don't worry, this was problem 24 from last year's AMC 12. So it's a pretty complicated problem, but with the law of cosines, it's actually very easy. If you already know the law of cosines, then you should go deeper into it. So we're gonna solve this problem with the law of cosines. Now before that, I want to tell you guys that it's very important to memorize the cosines, the sines, the sine, and the tangents of 15 degree angles, 30 degree angles, 45 degree angles, 60 degree angles, and other common angles, like also 120. Note that tangents, the tan does not have more than 90, but the other sines and cosines do. So for this problem, we still have to rotate it once to the other side by 60 degrees. So we know that this is 60. Now we know that this is also 60, as I told you before. And we also found out that by rotation, this became a 90 degree angle. And this became a 60 degree angle. That means we can use law of cosines here, because AC, pretend that is S. I mean, let's pretend it's A. So all it says is that A squared equals to one of the sides squared, which is 1 squared, plus 2 squared, which is 5, minus 2 times BC, which is minus 2 times BC, which is just 4, times the cosine of A, which is the cosine of 120. Now, the cosine of 120 is negative 0.5, I think. So A squared equals to 5 minus 4 times minus 1 over 2. Because that's the cosine of 120. That means this simplifies to negative 2. negative 2. Okay, so a squared equals to 5 minus 2. And the minus minus cancels out to a plus, so a squared equals to 7. And then you square root both sides to get a. So a equals to the square root of 7. That means the side length is the square root of 7. So the law of cosines can be very helpful, especially on the AMC 12. So if you're taking the AMC 12 and don't know the law of cosines, you should study it before the exam. It can be very helpful. And for those taking the AMC 10 and you know trigonometry, then you should learn the law of cosines and memorize the sines, the cosines, and the tans of common angles. The next problem. So whenever you have a very complicated figure, break the shape into multiple parts to find the answer. So in this problem, it says, Farmer Pythagoras has a field in the shape of a right triangle. The right triangle's legs have lengths 3 and 4 units. In the corner where those sides meet at the right angle, he leaves a small unplanted square so that from the air it looks like the right angle symbol. The rest of the field is planted. The shortest distance from S to the hypotenuse is 2 units. What fraction of the field is planted? Now remember that the shortest distance to the hypotenuse is always perpendicular to the hypotenuse, which means this is 90 degrees. Now we know that this is the hypotenuse, so it's 5. So the trick to this problem is connecting the vertex to the vertex of the square for both of the triangles. And then we use algebra. We assume we just substitute a variable for the side length of the square. Let's say it's x. So for now we know that the area of the entire field is 1/2 times 3 times 4, which is 6. The area of this region, this one, is 1/2 times 5 times 2, which is 5. That means this is 1. That means the area of this region is 1. And now we're going to calculate that region. So if this is x, what does that mean about the height? That means it's just 3 minus x. How about this side? If the whole thing is 4, that means you just subtract x from that. You get 4 minus x. Now we know that now we're going to use some algebra. So 1/2 times 3 minus x times x plus 1/2 times 4 minus x times x plus x squared, because you have to forget to add the square to it, equals to 1. So now let's simplify this out. Now before simplifying, let's multiply both sides by 2 to make the computation a lot easier. Yeah, so which is x squared, the other square, it's over here. I added the length of it. So we have x squared already over there. So we know that, so now we're going to multiply both sides by 2 to remove the denominator. So we get 3 minus x times x plus 4 minus x times x plus, you also have to multiply, if you multiply the denominator by 2, then it's 2x squared, and 1 times 2, which is 2. Now we will simplify this to get 3 minus x squared plus 3x minus x squared plus 4x minus x squared plus 2x squared equals to 2. Now, negative x squared minus 2x squared plus 2x squared, they're gone. Now we get 7x equals to 2. That means x equals to 2 over 7. That means the side length of the square is 2 over 7. That means the area of the unplanted region is 2 over 7 squared, which is 4 over 49. Now to find the ratio of what fraction of the field is planted, we know that the area of the entire field is 6. So the area of the planted region is 6 minus 4 over 49. So now it's time to compute that. So you take the LCM, which is obviously just 49. And then by 49 times 6, it's just 294. 294 minus 4 over 49. And you get 290 over 49. That is the area of the shade of the region that is planted, but we want to find the fraction that is planted. So you divide this by the area of the entire region. 290 over 49 divided by 6, so we can just say times 1 over 6 since it's the same thing. So after that, you see 2 is a common factor, so it reduces now. So 145 here. So 145 over 49 times 3, which is 147, and that is the answer. So this shows the power of connecting vertices to other points, and then trying to break down the problem into multiple shapes, and then finding the answer. So now let's move on to a 3D dimensional problem. So the goal of a 3D dimensional problem is to turn it into a 2D shape. In most cases, this can be done by looking at the cross-section. The only part that you have to be careful about is realizing what to take the cross-section of. So in this problem, we're going to learn that part. So it says a pyramid has a square base with a side length of 1 and has lateral faces that are equilateral triangles. A cube is placed within the pyramid so that one face is on the base of the pyramid and its opposite face has all of the edges on the lateral faces of the pyramid. Now it's asking us to find the volume of the cube. Well, the important part to notice about this figure is that if the base has a side length of 1 and it's a square and the lateral faces are equilateral triangles, then they also have a length of 1. Now, if you're thinking about slicing the 3D dimensional shape from half over here, you could do that, but that's actually a lot more complicated because we don't have the length of this line. But in some cases, you don't have to just directly cut it in half. Maybe you can cut it from here, from over here. And if you do that, we already know the lengths of that triangle, which is 1 in this case. And we know that if you look at the bottom base, this is also 1 and this is 1. That means this thing is just 1 squared plus 1 squared, which is 2, and you square root that. So this thing is just square root of 2. And simply, this is a 45-45-90 pair. So this is not this is 90, and this is 45, and this is 45. We also know that this is 90 because this is obviously a rectangle, and this is 45, and this is 45. This is 45, and this is 45. So there are lots of 45 and 90 triangles. So let's try to solve the problem. We don't know the length of the cube, so let's say it is S. So we know that this length from here to here is just the height of the cube, S. And this is S. This length over here, this thing, is not S. That's the most important part to realize. It's actually S times the square root of 2. Because if we cut it the diagonal, we took the diagonal of the square's base, which is S times S. So S squared plus S squared, 2. And then you square root that. So it's actually S times the square root of 2. Now, if the side opposite to 45 degrees is S, we know that this is an isosceles triangle, so this is S. So this is also S. That means S plus S, which is 2S, plus S times the square root of 2 equals to the square root of 2. Now you factor S from both sides, you get S times 2 plus square root of 2 equals to the square root of 2. Now we will divide both sides by this, so S equals to square root of 2 over 2 plus the square root of 2. Now all you do is now rationalize the denominator by taking the conjugate. The conjugate can be taken by just taking the opposite, just write down 2 plus square root of 2, except you reverse the symbol. So it's 2 minus square root of 2. So you multiply that to both sides. The top becomes 2 times the square root of 2 minus 2, and the bottom becomes 2 times 2, 4, minus 2, which is 2. And now this reduces to, the 2's cancel out, this becomes a 1. So the side length of the cube is just square root of 2, that BA times, PA times PB equals to PC times CD. So the length outside the circle times the full length equals to the length outside the circle times the full secant. And that's the 2 secant theorem. So now a problem, a very basic problem, but a good application for power of a point. So in a circle, we have chords AB and CD. Now we know AR to BR is 1 to 4. So this is X, then this is 4x, and CR to DR, and if CR is 4y, then DR is 9y. That means, and then it says find the ratio of AB to CD, and AB is x plus 4x, so 5x, and CD is 4y plus 9y, so we want 5x over 13y, and we can find it. Now we're gonna try to find this. So we know that the chord theorem that we learned states that so the place where it cuts it, so like 4y times 9y, so 4y times 9y equals to x times 4x. And now you compute this to get 36y squared equals to 4x squared. Now you divide both sides by y squared and then by 4, like first by 4, so you get 9y squared equals to x squared, but then you divide it by y squared, so you get 9 equals to x squared over y squared. And now you take the square root of that and you get x over y equals to 3. And then you multiply both sides by y to get x equals to 3y. And now you substitute this here to get 5 times 3y, which is 15y over 13y. And these y's cancel out, and you get 15 over 3. Now this shows that 15 over 13. This shows that power of a point is actually important, and it can help you find some lengths of chords, secants, and tangents. So now it's time for a small raffle. I'll be sending the link to it in the chat very shortly. Just wait like 2 minutes and I'll be sending it. Yeah, so there will be 2 prizes. There will be the same thing. It'll be an hour extra, like a private lesson from Explore Math, and on any concept that you want to learn. There will be one today and one tomorrow, and 2 winners for both. And also a 5-minute small break, and after that we'll work on number theory, which is our next part. Yep, and after you guys sign up and after a small break, we'll be working on number theory. It'll go on for another hour, and then we'll take a break. We'll end, and then tomorrow we'll have part 2, which will be probability and combinations and algebra in it. I'll be sending the link to everyone who registered. I'll also be posting it on AOPS for other people who didn't register and forgot. Just one important thing I recommend to you guys when you take the AMC 10 and AMC 12 is do not panic. Like, panic can cause people who are good to even do really bad. And the handout will be sent tomorrow after part 2 of the seminar. Okay, we'll be resuming in just 1 to 2 minutes now. Okay, guys, let's resume. Let's resume now. So number theory. So number theory, one of the most very common topic is modular arithmetic. So if you've ever, so the number in the parentheses that like mod 2 that I wrote here, it just represents the number that we divided it by. So if you ever see something like this, 4 there are 3 signs like this, 4 equals to 2 equals to 0 in mod 2. All this says is that if you divide all 3 of these numbers by 2, the remainder is the same. And indeed that is true, because 2 times 2, 4 plus 0. So the remainder is 0. Same for this expression here, it's also 0 here, and also 0 here. So it works with remainders. Modular arithmetic is mainly about remainders. And you'll see later on with the examples that we're about to show. So now, some properties. So for example, if we have A is equals to B mod M and C equals to D mod M, then these properties will always be true. And I will show you with some basic examples. For example, pretend we have 2 equals to 4 in mod 2, and then we have 3 equals to 5 in mod 2, which is indeed true because the remainder is 2 for the first case and the remainder is 0 for the other case. So these properties state that 2 to the power of 3 will be congruent to 4 to the power of 5 in mod 2. Note that the mods have to be the same. The number dividing in both of the cases have to be the same for these properties to be true. Now the next property states 2 plus 3, 5 is congruent to 9 in mod 2. All this means is that the remainder, when you divide both of these numbers by 2, it's always the same. And indeed that is true. 5 divided by 2 leaves a remainder of 1. 9 divided by 2 leaves a remainder of 1. Now for this next case, A minus C equals to B minus D in mod M. So this states that 2 minus 3, which is negative 1, is equals to negative 1 in mod 2. And one important thing to remember is that in modular arithmetic, you can work with negative numbers. For example, pretend I have negative 1. This equals to 4. This equals to 9 in mod 5. And then you can go down by 5. You can go to negative 6. You can go to negative 11. You can go to negative 16. Which is why this makes modular arithmetic powerful, because you can work with negative numbers. Later in the example, you will see that it's very important to know. So this next theorem states that 2 times 3, 6 equals to 4 times 5, 20 in mod 2. Just remember these theorems because they're very important in modular arithmetic. So now, this problem is a very, very good example of basic modular arithmetic and pattern recognition. Whenever you see the word remainder on a problem, you should start thinking about number theory and modular arithmetic and hunt for patterns to try to find the answer, and then look for places to apply modular arithmetic. So in this problem it states, let ace of 1, ace of 2, ace of 3, all the way to ace of 2018 be a strictly increasing sequence of positive integers, such that ace of 1 plus ace of 2 plus ace of 3 plus ace of 2018, all of those numbers, equals to 2018 to the power of 2018. Now it's asking us to find the remainder of ace of 1 cubed plus ace of 2 cubed plus ace of 3 cubed plus ace of 4 cubed all the way to ace of 2018 cubed divided by 6. Calculating this by hand would be insane because this number is just monstrously large. It's just not possible. So now we obviously can't do that. So we have to look for a pattern. So let's say that if we have a number that is 0 in mod 6, a number that is 0 in mod 6 means it's just divisible by 6, since it leaves a remainder of 0 when divided by 6. So 0, if you cube 0, you're obviously just going to get 0 after in mod 6. I'm not in mod 6. And I'll just make an arrow to represent all of the mod 6s since I don't want to write all of them down. So if you have a number with a remainder of 1, then this equal, and if you cube that, you'll get 1, which is just 1 in mod 6. The best part about number theory is that if you cube a remainder, then that will be the remainder after you divide by 6. If you do 2 cubed equals to 8. And in mod 6, that is actually just 2. So they're also equal. Now 3. Now if you take 3 and you cube it, 3 times 3 times 3, 27. You divide by 6 and look at the remainder. It's again 3. I'm starting to notice a pattern. 1 equals to 1, 0 equals to 0, 2 equals to 2, and 3 equals to 3 in mod 6. Now let's look at 4. 4. Now if you cube 4, you get 4 times 4, 16 times 64. And if you divide this by 6, you still get a remainder of 4 in mod 6. Now let's look at 5. 5 times 5 times 5, 125. You divide this by 6, you still get a remainder of 5. Now we don't need to look at 6 because 6 is the same thing as 0 in mod 6. So we're not going to do this forever. Now we notice that whatever number you put in, the remainder will be the same in mod 6 after if you cube it. Now that tells us that 2018 to the power of 2018, we don't even need to find we don't even need to cube the expressions because the remainder of this divided by 6 will be the same as the remainder of this divided by 6 because we just tested it out. And 2018 to the power of 2018, now we want to find that in mod 6. So 2018 to the power of 2018 mod 6. 2016 is divisible by 6, which means 2 is the left out remainder. So 2 to the power of 2018 in mod 6. And that's literally what we want to find. Still, this number does look monstrously large. So again, we will try to look for a pattern again. 2 to the 1 equals to 2 in mod 6. 2 to the 2 equals to 4 in mod 6. 2 to the power of 3 equals to 2 in mod 6. That means if you divide it by 6, the remainder is just 2. 2 to the 4 equals to 4 in mod 6. It's cycling. The remainder is 2, 4, 2, 4, 2, 4. And for every odd power, it's 2. And for every even power, it's 4. And in this case, 2018 is an even power. That means the remainder is 4. So this shows the importance of looking at patterns, writing some of the terms out and testing it, and then you will find the remainder after. And now we will look at a pretty similar example because the remainders always cycle, and it is very important to know this to look for pattern. It's literally just pattern hunting, and remember that the pattern will always be like that. So and then do it for the full routine because the 2010 is the highest power, and that's where we stop. And this was the point 1 and 3, and that means the remainder is just 4. Okay, now the next problem. Now this is also very important because modular arithmetic does not only work in addition, but it also works in multiplication. And the pattern is pretty simple, similar to addition. So in addition, we would add all the remainders, but in multiplication, we will multiply all of the remainders. So 9 times 99 times 999 times all the way to 999 nines. Finding this by hand, that's not possible. So then we need to use modular arithmetic because it's asking for the remainder. So 9 in mod 1000 is just 9 times 999 minus 99 times 99 I mean. And then we notice the other terms after 999. If you add 1 to that, it's always divisible by 1000. That means all of them are just -1 in modular arithmetic. And that's the best part about modular arithmetic. I can use negative numbers here. I know that if you pretend the remainder is 999, but that's also equivalent to -1 in mod 1000. So we know all the numbers, including 999, all the way to the end, will be -1 in mod 1000. And this has 3 nines all the way to 999 nines. So the number of times where the remainder will be -1 in mod 1000 will be 999 minus 3 plus 1, which is 997. So we note, so -1 to the power of 997 is obviously -1. So 9 times 99 times -1. And we want this in mod 1000. Okay, so 99 times 9 brings in 891 times -1, which is, so that means the remainder is just -891 in mod 1000. And the way to simplify this is you can subtract 1000 from it to find or you can add 1000 to it. And obviously, we want the positive number. So 891, and you add 1000 to it, that's equivalent to 109 in mod 1000. And that is the answer. So this shows the power of modular arithmetic. You can deal with immensely large numbers and find the remainders with just some simple computation. So it's very important to know. So now let's move on to the Euler's tangent function. So pretend if you want to find the number of numbers that are relatively prime to a number, maybe you're going to list them out. Furthermore, looking below at this theorem, I can understand it's pretty complicated to learn. When I first saw this, I thought it was calculus, so I just didn't even bother coming back. But it's actually a very simple theorem that I will explain. So the goal of the function is to find how many numbers are relatively prime to the number that we are using. And relatively prime means that the GCD between the given number and the chosen number is 1. Now, if you don't get it, don't worry, because the example I'm about to show you will clear it up. So pretend we want to find out the number of numbers that are relatively prime to 48, and we'll do that by looking at the numbers below 48. So maybe you're gonna start out by listing 1, and then you see 2 doesn't work, 3 doesn't work, 5 doesn't share. 5 has a GCD with 48 of 1, 7, but this is gonna take way too long, and you might make a mistake. But the Euler's tangent function states that if you take the prime factorization, first take the prime factorization, and 48 is just 2 times 2, 48 times 2 times 3. 48, if you prime factorize that, it's just 2 to the power of 4 times 3. And now the Euler's tangent function states that you just take this thing and this thing. You don't bother about the powers. We do not care about that. Now you take 48 and you multiply this by 1 minus 1 over 2 times 1 minus 1 over 3. You just take this number, take the reciprocal of that, and subtract it from 1. And for all the prime divisors, just prime. So then after that, we'll find this out. So 1 minus 1 over 2 is just 1 over 2 times 1 minus 1 over 3 is just 2 over 3. These 2's just cancel out. So 48 divided by 3 is 16. That means there are 16 numbers that are relatively prime to 48. So instead of actually computing it, look, it was so simple with this function. Now I have another very, very important theorem and a very good problem to show an example for it. So the Fermat's little theorem. This theorem states if a number, pretend you're dividing it by it has to be a prime number that you're dividing it by. So let's pretend mod of let's say 7. So mod 7. Then this states that anything to the power of 6, as long as it's not a multiple of 7, it will always equal to 1 in mod 7, which means if you divide it by 7, the remainder will always be 1. This works for 1, this works for 2, this works for 3. 3 to the power of 6 will always equal 1 for 5, 6, but not for 7, not for 14, because this number over here, these numbers, this a in this case, cannot be a multiple of the prime number that we're dividing by. You have to remember that part. That is the most important part about this theorem. So in this problem, it states an integer n is selected at random in the range 1 to 220. What is the probability that the remainder when n to the power of 16 is divided by 5 is 1? So this problem, instead of actually looking for patterns, Fermat's little theorem makes it very simple. So sorry for this line. So we're looking at numbers in mod 5, because clearly it says divided by 5. So in mod 5. So if you have a number that is not a multiple of, so an integer n, so this theorem states that n to the power of 4 is equals to 1 in mod 5. And it says we raise it to the power of 16. The best part is that if a number has a remainder of 1 divided by 5, and we're raising that number to the power of 4, this will also have a remainder of 1 to the power of 16. Because in modular arithmetic, you can raise it to powers. And if you raise the left side by a power, you raise the right side by a power. So for example, if you take n to the power of 4, and you raise it, and pretend it's and then you raise it to another power, which is 4, to get n to the power of 16. Then that means the remainder is just 1 to the power of 4, which is obviously just 1. That means That means we can just look at this in n to the power of 4. And in n to the power of 4, this will only be a remainder of 1 if the number n is not a multiple of 5. And in 1 to 220, the only numbers that are not multiples of 5 are 1, 2, 3, 4. You skip 5, 6, 7, 8, 9, 10. You see what I mean? For every 5 numbers, you skip 1. So out of every 5 numbers, 4 will always have a remainder of 1. So that means the answer is just 4 over 5. So this just shows the power of Fermat's little theorem, because we simplified a pretty scary looking problem. Since pretend you took 220 to the power of 16, it's kind of scary, like 219 to the power of 16, but with modular arithmetic, it was pretty easy for us. Now on the next problem, it's an AMC problem 13, so it looks hard at first. So this problem states that the numbers in the sequence 101, 104, 109, 116 are of the form 100 plus n squared, where n equals to 1, 2, 3, all the way forward. Now for each n, we want d of n, which is the greatest common divisor of a of n and a of n plus 1. Now we want to find the maximum value, so as it ranges to positive integers. So this problem might be hard to understand. I'll explain it. So we have 100 plus a perfect square of all the way from 1 plus 2 squared plus 3 squared plus 4 squared plus 5 squared all the way. And we will take 2 consecutive terms. For example, you can take these two, you could take these two. They have to be right next to each other. You can't take 109 and 101. That's the main part you have to notice in this problem. So if a of n equals to 100 plus n squared, then notice that to get the next term, it's just 100 plus n plus 1 squared. So now comes the Occluding algorithm. This states that the GCD of two numbers a and b, in which a is greater than b, it's the same thing as b and a minus b. Finding the GCD of that, which it's very helpful in simplifying. Like if you have two big numbers and you want to find the Occluding algorithm of it. So this problem can be very helpful in those cases. So 100 plus n plus 1 to the power of 2 simplifies to 1 squared 1. You add that to 100. 101 plus n squared plus 2n. So we want to find the GCD of 100 plus n squared plus, not plus, sorry, comma here. And 101 plus n squared plus 2n. Now we want to find the GCD of this. Now we know that by subtraction, we can subtract these two equations to get n squared plus 100 over 2n plus 1. Because if you subtract it, you notice, like I subtract the smaller one, we know this is smaller. So we subtract this from this, and we know n squares cancel out. The 2n just stays there as 2n. 101 minus 100 is just 1. And then we take the smaller term, not the bigger one. We disregard that. We do not care about that. So now, this can actually, the best part about the Occluding algorithm is that you can multiply it by a number and then subtract it. For example, if I have a and b, then I can also do a and 100 times b in some cases. To like pretend a is 100 and b is 1. Then you can multiply it by 1000 to simplify it, and then you'll get 0, which means there is no, that the GCD is just 1. We will do something similar in this case. We know that if we can remove this 100 from here, then it'll be pretty simple after. And that's our goal. It's to get rid of this 100 term. And this can be done by multiplying the second term by 100. So this is the same thing as finding the GCD of n squared plus 100 over 100 times 2n plus 1. N squared plus 100 minus, sorry. And you want to find the GCD of this thing along with 2n plus 1. Yep, 2n plus 1. And then you simplify this, and you see hundreds cancel out, and you're just left with n squared minus 200n and 2n plus 1. And the most important part of the problem is that there is a GCD. Like if you look at these two numbers, n is a common factor. However, n will never divide 2n plus 1. You can try proving this on your own, but obviously if n is 1, like not 1, like pretend it's 2, and you put 2 in here, you get 5. It's never going to divide it. N will never divide 2n plus 1. So we can just factor the n out. So this is n minus 200 and 2n plus 1, because we know n will never be a factor of 2n plus 1. And that is like literally the most important thing that you have to notice in the problem. Now we want to get rid of the 2n term. Now we can do that by multiplying the left side by 2, and you get 2n minus 400 over and 2n plus 1. Now we find the GCD of these two terms, and this can be done well, pretty simply by so you subtract it now. So 2n's cancel out. 2n plus 1 minus 2n minus 400. The minus becomes a plus, so 401. And 401 along with the smaller term, which is just n minus 200. And at the end, you have n minus 200 and 401. And you want to find the GCD of this. And which is clearly just 401. And you can test it out. It will always be 401. In the Occluding algorithm, if you ever find an integer value and some linear term here, then it's always the integer value will be the GCD. And that's how we found it. If you don't understand, you can come back to it later, and the handout will have examples and explanations to like and this theorem more in depth, so you can use that, and then later you probably understand this. But even if you don't feel bad, because this was an AMY problem 13, so it's pretty complicated, obviously. The next problem, even though it's from IMO, it's actually very easy. Now we want to prove that the fraction 21n plus 4 divided by 14n plus 3 is irreducible for every natural number n. Now, if a number is irreducible for every natural number n, what does that mean? That means the GCD of the two terms needs to be 1, and that will be the only case. So that means we want to find 21n plus 4 over 14n plus 3. We want to find the GCD of this, and if the GCD of this is 1, then we know that this is irreducible. So now we take the smaller term and subtract it from the bigger term. In that case, 21n plus 4 minus 14n plus 3, we get 7n plus 1. And then we take the smaller term from the top equation, which is just, not equation, but just the terms, and 14n plus 3. So now we want to find the GCD of these two terms. Now we use the Occluding algorithm again, and then you subtract the smaller term from the bigger term. Clearly 7n plus 1 is smaller. So after that, you get you subtract this, and you get 7n plus 2 over 7n. I mean 7n plus 1. Yep. Now you want to find the GCD of these two numbers. Now if you subtract them directly, you subtract the smaller term from the bigger term. 7n plus 2 minus 7n plus 1, the plus and minus becomes a negative sign. So 7n plus 2, the GCD of 7n plus 2 minus 7n plus 1 over, and 7n plus 1, because you take the smaller term from the other side. So the GCD of this, we want the GCD of this. And clearly the 7n's cancel out, and 2 minus 1 is just 1. So we want to find the GCD of 1 and 7n plus 1. But we notice that we got 1 here, which means we want to you can't find the GCD of 1 in another number. It's obviously going to be 1, which means that it is irreducible. Okay, now this is more into modular arithmetic and applying the theorems that we learned before in the beginning of class. And now we're going to apply those theorems to solve problems that are purely based on those theorems. So it says, when each of 702, 787, and 855 is divided by the positive integer m, the remainder is always the positive integer r. When each of 412, 722, and 815 is divided by the positive integer n, the remainder is always the positive integer s, which is never equal to r. Now we want to find the sum of m plus n plus r plus s. So we know that we want 702, and the remainder is r in mod m. we have 787. 787, it's equals to its remainder in just mod m. And that's same for 855. 855 equals to r in mod m. Now in this case, if you remember the theorems that we learned, if you have some statement that is then you can just subtract the terms, like a equals to b in mod m, and if you have a term that is c equals to d in mod m, then you can just subtract a minus c with and b minus d to get to go further in mod m. So in this case, we subtract 787 and 702. That means this thing is equivalent to, that means 85. If you divide 85 by the mod m expression, you get 0 because r minus r is 0. That means 85 is a multiple of m. Now we do the same for 855. If you subtract 787 from that, you get 68. And we know that r minus r becomes 0. So 68 equals to 0 in mod m. Now, we start to notice something. If both of these numbers are divisible by m, that means we need to find the GCD of 68 and 85, which is clearly 17. And we know that m is 17. You can use the Occluding Algorithm yourself and find the GCD of 85 and 68, but it is 17. We know m is just 17. Now we're going to divide 702 with 17 to find r. And we get 5, and 5 is the remainder. So that means r equals to 5. So now we will do the same process, except for now the next terms, which are n divided by the positive integer n and with the remainder of s. We will do the exact same thing. But instead of writing it out now, we know that if we just subtract these terms with each other, then the remainder will be 0 in mod n, which means 722 minus 412, which is 310, and 815 minus 722, which is 93. They all have to be 0 in mod n. And this will work by taking, now all we do is take the GCD of both of these numbers to find what is n. And if you do that, you'll find that 31 is the GCD. And we know that that's the GCD, so that is the number we're dividing by in this case. And now we will do this, now the remainder is not 0, note that, because that was when we subtracted the remainders, which made them 0. Now we actually divide 31 from one of these 3. We'll divide it from 412 to find the remainder, which was s. We want to find what s equals to. So 412 divided by 31. So after you divide it, you get s equals to 9. Now it says find m plus n plus r plus s. And after you add all of these terms, you get 31 plus 9, which is 40, plus 17 plus 5, which is 22, which equals to 62. But this is the aim, so we write a 0. So 0 and 62. So this shows the power of applying modular arithmetic properties, and it made this problem pretty simple. So now our next problem. Now this brings in another concept. Now divisors. To find the number of divisors of a number like n factorial, and you want to find the number of divisors of, like, pretend p is a prime number, and all you do is you divide this by p. You just take n without the factorial. Then you add p squared to it. And you pretend I want to find 5 factorial, and I want to find how would the greatest power of 2 that goes into 5 factorial. So all I do is I divide 5 and 2 plus 5 and 4, and 5 and 8, there is no integer value of that, so we don't care about that part. So in this case, 5 over 2, we just take 2 because we take the 4 function, because it only has 2 powers in this case, and in this other case, it has 1 power. So there are just 3 powers. So now we will use this method to find the the number of perfect squares, the divisors of the product of 1 factorial times 2 factorial all the way to 9 factorial. So now we will have to find out the prime factorization of that those terms above, which will be pretty weak. Pretty hard, but we'll manage. So 2 factorial. This is just 2. And how many factors of 1 are there? 1. Note that I'm just writing the number of powers of 2 we have. 3 factorial. 3, and then we also have the prime number 5, and we have the prime number 7. So we want to find the number of the exponent that goes above it. So there, this term 2 just has 1 factor, obviously just 2. 3 is 3 times 2, so 1 goes to 3 and 1 goes to 2. Now 4 factorial. To find the number of primes to find the highest power of 2 that divides it, we divide this by 2, it's 4 itself, and then we divide 4 with 2 squared, and you get 3. And you do the same for 5 factorial. 5 over 2 plus 5 over 2 squared. But you just take you round down always. So 5 over 2, 2.5, we always round down. 2 plus 1, 3. Oh, in 4 factorial, I forgot to take the power of 3. So we also have to add that power of 3. So now, for 5 factorial, we have 1 factor of 3, and then we have 3 factors of 2. And we also have 1 factor of 5. So now we're going to move on to 6 factorial. 6 factorial, how many factors of 2 does it have? Just take 6 over 2 plus 6 over 2 squared, and we get 4. So it has 4 powers of 2. Now we will do the same for 3. 6 over 3 plus, we can't square that, well, 6 over 9, there's nothing for that, so just 2 factors of 3. Now we'll do the same for 5, which is clearly just 1. 6 over 5 for function 1. Obviously 7 is not a divisor of 6. So now 7. 7 over 2 plus 7 over 2 squared. And if you cube it, it's 7 over 8, and the full function is just 0, so we don't care about that part. 7 over 2, the full function 3. 7 over 2 squared, 4, just brings in another 1. So 4, another 4 here. Now we'll do the same for 3. And I'll just skip through this part because this is just boring computation. So you get 2 here again. For 3, you get 1 here and 1 here. Now for 8 factorial. We'll have 4 powers from just 2, plus 2 powers from 4 squared. For 2 squared. And then 1 power from 2 cubed, which brings it to 7. Now we'll do the same for the powers of 3, which is clearly just 2. Plus 2 here. And then for 5, just clearly just 1 power of 5 in 8 factorial. For 7, it's just 1 power, because you just keep using this method. And now we take 9 factorial, finally our last term. So 9 over 2, just 4, and for function 9 over 2 squared, which brings it to 2, and 9 over 2 cubed brings it to 1, which makes it 7. And then we do the same for 3, you get 4, you do the same for 5, you get 1, and the same for 7, you get 1. And now we'll get to the real problem solving. So 2 to the power of, we add all of this up, 2, 5, 8, 12, 16, plus 4, just 2 to the power of 30, times 3 to the power of 13, times 5 to the power of 5, times 7 to the power of 3. And now in this case, if we want to find the number of perfect squares that divide this, there is one method to this. So all we do now is, we know that if it's a perfect square, I'll show you a way to rewrite this in a way so that we can calculate it. So if it's a perfect square, it's the exponent is always going to be a multiple of 2. So let's say 2 to the power of 2a times 3 to the power of 2b times 5 to the power of 2c times 7 to the power of 2d. Now we know the a term goes all the way to 15, because if you add something more than 15, it'll become 2 times 16, which is 32, clearly more than 30. So 15 is the max we can go. But do not forget that you also have to count 0. That is the most important part. It's like technically counting the number of divisors. Technically, you can say that. So it's 16 times 2 times the max power that you take to go here. You can't have 7, that's more, so you have to have 6. And 0 to 6, which is obviously 7. There's 7 terms in it. And then times, you do the same for 5, and do the same for 7. You get 3 and 2. And if you multiply this, you get 672. If you don't understand this right now, it's perfectly fine. The handout will make it a bit more clear about how to compute stuff like this. So now comes in our next topic, Diophantine equations, which is kind of similar to Simon's favorite factoring trick. And then this is all about transforming an equation into something factorable. For example, an example of a factorable equation is just xy plus 3x plus 4y plus 10. Equals to 10, because we can actually factor this by adding an integer to it. A linear example is 5x plus 6y equals to 10. And then this comes from ax plus by equals to c. Now there are more Diophantines like elliptics, but that's not even at the AMC 10 and AMC 12 level, so there's no need to worry about this. So now this problem is full of Diophantine equations, and now let's try to crack it out. Now we know that ab plus a, we can factor this by taking out a. So a times b plus 1 plus, we want b to be factored, and we notice we want b plus 1 here, so a can actually be added to this term over here. So a 1 times b, and then if you make this exact term, you add it here, b plus 1. A times b plus 1 plus 1 times b plus 1, that means you add 1 to both sides to be able to factor this into a plus 1 times b plus 1, which equals to 500 and equals to 525. Now you do the same for the next example. For the next part, you take a b. You notice that this is just b times c plus 1 because of these two terms. Now we want c plus 1 to be here. This is possible. You multiply you multiply this by 1, and then you add an extra 1, so this equals to 147. But you can just add b because this thing is the same here and here. So b plus 1 times c plus 1 equals to 147. And note that Simon's favorite factoring trick works when you have two variables multiplied to each other, and then those variables isolated after. Then you can use Simon's favorite factoring trick to solve the problem, and it's a very important method. Like in this problem, it's very important. So now we'll do this for the next one, and we'll get c plus 1 times d plus 1 equals to 105. Now I'm gonna write this in a text box, so it's a lot neater. So we have a Okay, so now we wrote this into text boxes to make this problem a bit easier to understand now. So now we have these three equations. Now we need to find a way to factor it. Now, the important part to notice is that b plus 1 is over here, and c plus 1 is over here. So now that means there will be some common factors between these two equations. And all of these three equations, there will be some common factors. So we notice that 525 is just, you prime factorize it, 3 times 5 times 5 times 7. This thing is 147 is just 3 times 7 times 7, and 105 is just 3 times 5 times 7. Now what I mean by this example is that, well, like c plus 1 cannot be 15 because 15 does not divide 147. So it has to be some shared factors between these two parts. And it seems easier to work with b plus 1 times c plus 1 because both of these terms are they're intersected by the other things. So 3 times 7 and 3 times 7 is also here. So maybe b plus 1 is 3 times 7. So we'll try that part now. b plus 1 equals to 21. A plus 1 equals to 25. C plus 1 equals to 7. And d plus 1 equals to 15. And after that, if you compute this, you get A equals to 24, B equals to 20, C equals to 6, and D equals to 14. And then also this does multiply to 8 factorial. Computing 8 factorial right now will take a long time, but in this problem you might have to do some this is a trial and error at the end. For example, you put in b plus 1 equals to 7, then b plus 1 equals to 3 times 7, and after that, that's when you get the answer. So even if you actually try it out, your first case will be b plus 1 equals to 7, then 3 times 7, and after that you get the answer. But at the end, we just skip through that part because that's just a lot of computation, and we have to go through the theory. So we get 24, 26, and 14, which is A, B, C, and D. And then 24 minus 14 is what it's asking for, which is 10. And then this example shows the power of Simon's favorite factoring trick, because it was used to solve this very complicated looking problem. And then Simon's favorite factoring trick made it pretty easy for us. So now, our next problem. Now, sometimes before you form complicated Diophantine equations, you should play with the equation before, since there might actually be a simple solution to finding the answer to the problem. Now in this problem it says there is a prime number p such that 16p plus 1 is the cube of a positive integer. Now it wants us to find p. So in this problem, let's say that we want to find, let's say that the number we want is n cubed. And it says that 16p plus 1 is just the cube of the integer. So we can just set this equal to 16p plus 1. Because this thing is a cube of an integer. So let's say n cubed is equal to that. Now we subtract 1 from both sides to get n cubed minus 1 equals to 16p. Now, remember, there are different ways to factorize, like n cubed minus 1. It's an important factorization to know. But n cubed minus 1 is factorized like this. N minus 1 times n squared plus n plus 1. The handout will have all of these important factorizations, so you don't need to worry about writing this down or memorizing it right now. So n minus 1 times n squared plus n plus 1 equals to 16p. Now comes the part where we have to think a bit. So there's 16 times a prime number p. The p has to be odd because 32 is not, like, the only even number prime is 2, and if you see 16 times 2, it's not gonna work. 33 is not a prime number, so we know 16p, so p has to be odd. And in that case, we will look at this term here. Pretend n is 1. Then that means n squared is 1. 1 plus 1 plus 1, which equals to 3. Now let's pretend it's an even number. 2 squared, which is 4, plus 2 plus 1 equals to 7. This means that n squared plus n plus 1 is always an odd number. And if you recognize this part, you will be able to solve the problem. So using a bit number theory, we notice that n squared plus n plus 1 is always an odd number, which means 16 does not divide it at all. Because 16 is just full of factors of 2. That means n minus 1 is 16, because n squared plus n plus 1 is p. That means if we set n minus 1 to 16, because we know 16 cannot divide n squared plus n plus 1, because n squared plus n plus 1 is an odd number, as I just showed you how. So n minus 1 equals to 16. That means n equals to 17. And then you substitute this here. You get so 16 times 17 squared plus 17 plus 1, which is just 2. We just divide both sides by 16, so we don't care about that part. So at the end we get 289 plus 17 plus 1, which is equal to p. And now adding 289, 17, and 1, that gives you 307, which is our answer. So this shows the power of like, actually, before you just try making Diophantine equations, substitute variables, and then you might find those factorization methods like this one, n cubed minus 1. It factors in this way, and that's how we found the answer. So now let's move on to our next problem. Now this brings in another important concept. Maybe like if you're taking the contest, like pretend you're taking the AMC 10, then you might not recognize that the GCD times the LCM is equivalent to the two numbers multiplied. I'll show you what I mean. So this concept says that if I have a GCD of two numbers and the LCM of two numbers, then if I multiply those, then that's just the other two numbers multiplied. For example, pretend I have A and B are my two numbers. So this thing states that A times B equals to the GCD of A and B times the GCD of I mean not the GCD, I mean the LCM of A and B. And this will always work no matter what. And it's something that is very important to know. Times the LCM of A and B. So the two numbers multiplied is just equivalent to the GCD times the LCM multiplied. So now, in this problem it states, how many ordered pairs A and B of positive integers satisfy the equation A times B plus 63 equals 20 equals to 20 times LCM of those two numbers plus 12 times the GCD of those two numbers, where GCD denotes the greatest common divisor and LCM denotes the least common multiple. So now, let's say that we know that A times B is equivalent to the GCD of A and B times the LCM of A and B. So now, let's say the LCM of A and B is X. And the GCD of A and B equals to Y. Now we can just substitute this in here because we know X times Y will equal to A times B in this case. So all this says is that X times Y plus 63 equals to 20 times the LCM, which is X, plus 12 times the GCD, which is Y. 20X plus 12Y. And now this is some now all we need to do is some factorization. So we know, using Simon's favorite factoring trick, we're now going to factor this out. So let's take the xy and the negative, you bring everything to one side. Xy minus 12y plus, minus 20x plus 63 equals to 0. Now you factor these two terms, and then y is the common term. So y times x minus 12, that's pretty obvious, that part. And in Simon's favorite factoring trick, you want this term to be here again. You want this to take a form of this, so you can add whatever number is here, you can add that to y to find the factorization. I mean the factoring method. So we want something here that so we want to find out what we multiply x by, and in this case that is 20 because we want the coefficient to be negative 20. So we multiply by negative 20, and then we get 240, which is an extra. Well, what I mean is that, like, if you do this method, I'll show you what I mean. So y minus 20 equals to, times x minus 12. Do you see the extra 240 we have right now? If you subtract, now we want to find out what number we subtract 240 by to get 63. And that number is 177. So you subtract this by 177 equals to 0. And this is the exact same thing as this equation, but this looks a lot neater. And now we will bring 177 to the other side. I'll erase all this so we can have some space to work. So now we have x minus 12 times y minus 20 equals to 177. And remember that x is the LCM and y is the GCD. So now we want to find out the prime factorization of 177. We notice that it's divisible by 3, so 3 times 59. So that's just the prime factorization. So we know that these two terms, we can take this as individual terms. So it's either going to be 3 times 59, or it's going to be 59 times 3, or it's going to be 177 times 1, or it's going to be 1 times 177. There was an option 4 for this, and before you bubble in option 4, think about the problem first. If you take x minus 12 equals to 3, then in this example, this will be 15, x will be 15, and y will be 79. In this one, if you put this in here, x will be 71, and y will be 23, because 23 minus 20 equals to 3, 71 minus 12 equals to 59, which is these terms over here. We do the same for this one. So 189 and 21. And we do the same for this other thing, 13 and 197. Now, this might make it look like there are 4 ways. However, you need to remember that the GCD of a number is always greater than the LCM of a number. And in this case, x is the LCM, and this y is the GCD. The only cases that will work are the cases in which the GCD is larger than the LCM. In this case, the GCD is larger. In this case, it is not. This case, it is not, but in this case, it is. So there are only 2 cases in which the GCD is larger than the LCM, which means the answer is just 2, which means there are only 2 ways. And now, thank you for watching, and remember that tomorrow is part 2 for the seminar. I will be emailing the link to join, and then tomorrow I will also be sending the handout to everyone. And don't forget that tomorrow we will be covering probability and combinations along with algebra, which are 2 very, very common things on the AMC 10 and AMC 12, which you guys need to know if you want to do well on it. And we will be covering that concept along with a lot of problems. So